Hi, welcome to this video. My name's Phil and I'm a senior lecturer in astrophysics at the University of Lincoln, and I want to go back to galaxies yet again, but this time to actually have a look at groups and clusters of galaxies and what the difference between the two is and how we can actually define what a galaxy group is and what a galaxy cluster is. So, for those of you who aren't aware of what a galaxy is, I'm assuming most of you probably know what a galaxy is, but if not, these are enormous systems of stars, gas, dust, also dark matter. In fact, some of them have quite significant amounts of dark matter where the vast majority of their mass is kind of dark matter, and they're held together by gravity. We have disk-like galaxies, we have more kind of spherical, ellipsoid shaped ones. There's a whole variety of different sorts of galaxies, but as a general rule, these are massive systems containing stars. Not all of them contain lots of gas and dust, again it depends on the type, and your dark matter held together by gravity. So on the Hubble classification system, you have this tuning fork, you have your spirals that kind of sit over to the right hand side, you can have normal spirals, barred spirals along the bottom, you can have intermediate spirals, which is not shown here, but they're in between the two, and they are they don't have a very strong bar, they have a weak bar, so they're intermediates. And then on the other side, we have our elliptical galaxies. These are mostly essentially ellipsoid in shape, and they're classified by how elliptical they look. They don't have the spiral arms like spiral galaxies, they have less gas. But those are the two main types essentially, but there's lots of different variations on that, and one of those just have spiral arms and features, and the other is a bit smoother looking. But we're not interested in the actual galaxy classification itself, we're interested more in how these galaxies behave on a bigger scale, in clusters and stuff. So most galaxies in the universe, they're not isolated. They're not just sitting there in space, evenly distributed in the universe. They tend to cluster together in gravitationally bound aggregations. So they kind of come together in these groups, these clusters, and they're not evenly distributed. And they got a really nice picture there actually of a galaxy cluster. And there's lots and lots of galaxies there. Pretty much every bright bit there is a galaxy. You've got lots of different sorts of galaxies. It's not necessarily an even distribution of galaxies. You might find that they have a higher density in the center and it drops off towards the outer part. But nonetheless, this is a cluster of galaxies that has been imaged, and it's quite a nice picture actually. So, how do we characterize if it's a group or a cluster? There's a few ways we can define when it's a galaxy group and when it's a galaxy cluster. And in order to define that, we can use these things here. So we can actually count the number of member galaxies. So that can be a threshold for whether it's a group or a cluster. Small amounts might be one, bigger amounts might be the transition point into the next classification. We've also got the size of spatial distribution. So essentially the size of the group, or the amount there. So let's say we've got like this kind of group of galaxies, cluster of galaxies. What sort of space is that covering? That could give us an indication as to which it is. Is it a group? Is it a cluster? We've also got internal dynamics. So this will be like the velocity dispersion. The relative movement of all those galaxies within the cluster itself can be used to actually find the definition between the two again. And also the total mass, which is going to relate to the number of galaxies in there and also kind of the size as well. So number of member galaxies. The threshold is around about 50. So less than 50 galaxies in one of these kind of collections, we would classify that as a group. And above 50, so typically between 50 and 1,000 member galaxies, it would then be classified as a cluster. So on the left-hand side, we've got a group there. There's actually 4 dominant galaxies there. And on the other one, we've got quite a significant cluster of galaxies instead, which has got a lot more member galaxies in. We can then use the spatial distribution as well. So typically, groups are going to be less than 1 megaparsec in size, regardless of kind of how many members are in there. And clusters are going to be greater than 1 megaparsec as well. So size can be used, and 1 megaparsec is typically kind of like that transition point between the two. Now, internal dynamics is another way that we can classify it. So the internal dynamics is looking at the velocity dispersion. So that's the movement of the galaxies within the cluster, and it's a bit randomized, and that gives us this velocity dispersion. So the distribution of the velocity of the galaxies. Now what happens here is that when you have more member galaxies, the total mass of the collection goes up, you get a greater distribution in the velocity dispersion, you get a wider spread in that velocity, so you get a greater velocity dispersion. And just to highlight that, you've got this here. So we could then basically put them as groups or clusters, and there'll be a threshold of around about 500 kilometers per second for that velocity dispersion when it goes from a group to a cluster. So groups will have velocity dispersions below 500 kilometers per second, and a cluster would be greater than that. And in fact, clusters are typically around about 500 to 2000 kilometers per second. And as you increase the number of galaxies in that, you increase the mass of the cluster, then that velocity dispersion increases as well. So there's a correlation between the internal dynamics and the mass of the total system. And if we actually know the virial mass, I'll mention what that is in a little minute, but basically if we know what that is, then we can also define it as a group or a cluster, and that threshold for the virial mass is about 10 to the 14 solar masses. So that is our transition point between a group and a cluster as well. Now how do we get that? Well, the virial mass comes from the dynamics essentially, so it comes from the virial theorem. And this is a principle that links the average kinetic energy of particles, which will be galaxies in this thing here, in a system to its average potential energy. So we've basically got galaxies in place of our particles, and it's their kinetic energy and their average potential energy in the cluster or the group itself. And we can then use that to estimate the mass based on the dynamics in that. So if we know that, we can then also kind of work out if it's a group or a cluster. So that was just a brief overcap of kind of what a galaxy group is and what a galaxy cluster is. And so thank you for watching. If you enjoy the videos, then consider becoming a member. There's extra videos in the member section, and it also helps support the channel as well. So thank you for watching.